Good morning, good afternoon from the International Society in Quantization, Geometry and Dynamics, ISQGD. ISQGD is a non-profit, community-driven global society dedicated to serving the worldwide mathematical and interdisciplinary research community, fostering excellence from K-12 education to frontier research. Today, the session is ISQGD SS06 topology and geometry. It is a pleasure to introduce our first speaker, Roberta Shapiro from the University of Michigan. The title of her talk is Geometry, Topology and Combinatorics of Fine Curve Graph. Yes, please.
Thank you for the introduction and for the invitation to speak. So without further ado, let's get started and I'll say how all these words come into play in a bit. Right. So one of the things that motivates me as a mathematician is an interplay between topology and combinatorics. And a lot of the times this connection is seen through algebra. So on the topology side today, we're going to be working with surfaces, while on the combinatorics side, we're going to be working with graphs that are built based on these surfaces. Okay. So what are these graphs? Right, so on one hand, we have a graph. It was introduced uh, probably somewhere in the 60s, and it's called the curve graph of a surface. So whenever we have a graph, we need to know what are the vertices, what are the edges. So the vertices here are the homotopy classes of essential simple closed curves. What does this mean? This means that a curve, just on its own, is an embedding of a circle into a surface, so two-dimensional manifold. And we moreover ask that these circles are essential, which means that they do not bound a disk in the surface. And finally, we put an equivalence relation on them, so homotopy classes. All right. Then, uh, what does it mean for two curves or two homotopy classes of curves to be connected by an edge? Well, two homotopy classes are committed by an edge, or are connected by an edge when they admit disjoint representatives. So, for example, if we look at the picture up here, we have a pink curve that I'm pointing to and a red curve that I'm pointing to. They are homotopic, so they correspond to the same vertex in our graph. Moreover, if we look at the red and the blue over here, they look like they intersect. However, since they can be homotope to be disjoint, they are actually connected by an edge. Right. So maybe we overcomplicated things. Maybe something got a little weird with the homotopy classes. So we can ask, what happens if we drop this condition of modding out by homotopy class? Uh, well, then in that case, that would be a graph whose vertices are just all essential simple closed curves, while two edges connect, or an edge connects two curves if they are disjoint. So this is called the fine curve graph of a surface. And although it seems like maybe we lost some of the more, uh, I guess, difficult part of thinking about curve graphs, which is the up to homotopy, we gained significantly more, which is we gained an uncountable number of vertices and an uncountable number of edges, whereas before our graph was purely countable. So we have this new object. It encodes something slightly different about the surface. Uh, but it is much bigger. And so one of the questions we can ask is, if the graph is bigger, does it actually hold any new information, uh, dynamically, combinatorially, etc., or are we kind of just stuck where we were? So let's see the first thing. So what do we know about these graphs? Uh, well, from on one hand side, we can ask about the geometry, which practically speaking asks whether these graphs are hyperbolic, or delta hyperbolic or Gromov hyperbolic, which really just means, all right, these graphs are metric spaces. You have vertices, and the distance between two vertices is the length of a shortest path. And whether these graphs are hyperbolic asks, all right, if we have uh, a geodesic triangle, so vertex, 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 the geodesic triangle, does it look sort of like a geodesic triangle in a hyperbolic space in that it kind of looks thin? What does that actually mean? Well, it means that there is a constant delta for your space, so that if you look at the delta neighborhood of any two, whoop, not that, any two edges, you contain the third edge. So that's how we can maybe translate this idea of hyperbolicity to hyperbolicity in just metric spaces in general. Okay. So the curve graph was first proven to be hyperbolic by Mazur and Minsky, um, and there have been multiple proofs since. Whereas the fine curve graph was proven to be hyperbolic much more recently, like 20 years later, by Bowden, Hensel, and Webb. So why do we care about hyperbolicity of these graphs? Well, if we have that these graphs are hyperbolic, we can do geometric group theory on them by seeing which groups act on these hyperbolic spaces. So which groups act? Well, when we have the fine curve graph with all the possible curves, we have that the group of homeomorphisms acts on our graph. In particular, homeomorphisms take vertices to vertices. So if you look at a curve, a homeomorphism will take a curve to another curve. And they take edges to edges because homeomorphisms, they because they're continuous and their inverses are continuous, they make sure that any two disjoint curves are sent to any two disjoint curves and vice versa. Okay. Um, on the side of the curve graph, though, we have that the extended mapping class group, which is the group of homeomorphisms, but up to isotopy or up to homotopy, acts on the curve graph for very similar reasons. So we have these two groups that, generally speaking, topologists are very interested in. And we want to know, how do these groups act on these hyperbolic spaces? Um, well, if we look at the action of the extended mapping class group on the curve graph, we'll see a couple kinds of actions come up. So one type is elliptic actions, which means that things don't really move too much. It's like the orbit of uh, any point in your space is bounded. There are some elements of the mapping class group that act loxodromically, which means that things move with linear speed, more or less, upon repeated application of your mapping class. And moreover, this is a very nice kind of dichotomy in that it respects a pre-existing classification of mapping classes based on how they act on a surface. So with that in mind, we can ask, all right, what do we know about how the homeomorphism groups acts on the fine curve graph? Um, well, there are still elliptic actions. So in particular, if you have something of finite order or the identity, well, that's not going to take things very far. Um, right? Then we still have loxodromic actions, but now there are actually loxodromic elements of the homeomorphism group that exist arbitrarily close to the identity, so that are homotopic to the identity homeomorphism and exist in any open neighborhood of the identity. So that's maybe something that starts to get a little surprising because it's very, very different from what's going on in the mapping class group and curve graph case, which is well established. Uh, moreover, there is a third type of dynamics that we see when we act by homeomorphisms on the fine curve graph, which is we see some parabolic elements, which means that yes, the like different vertices have unbounded orbit, but things move at a sublinear speed. So that's completely new when we talk about the dynamics of homeomorphisms on the fine curve graph. And it indicates that the dynamics of the action here with the homeomorphisms are much richer than the dynamics down here with the mapping class group. So perhaps we have something to learn from these. And in fact, when we restrict ourselves to smooth curves and we have the diffeomorphism group acting on the fine curve graph, on the smooth fine curve graph, we get that diff naught of our surface, which is all diffeomorphisms isotopic to the identity, actually admits unbounded quasimorphisms, which is pretty different when it comes, when it comes to manifolds of various dimensions. And this is for compact surfaces. So here we have this very unexpected almost result for diffeomorphism groups that was obtained by Bowden, Hansel, and Webb. With that in mind, this came, in the first paper about fine curve graphs. This leads us to be motivated by to study fine curve graphs because perhaps we can learn more about homeomorphisms or diffeomorphisms from their actions and from the structure of the fine curve graph itself. So with that in mind, we can move on to the combinatorial structure. So we're going to go bottom to top here. So a more well-known theorem is a theorem of Ivanov, Korkmaz, Luo. There are several others who also proved theorems in a similar direction. And it's that if we take a look at the automorphism group of the curve graph, well, it is actually naturally isomorphic to the extended mapping class group. And this natural map is actually the action of the extended mapping class group on the curve graph itself. Right. Uh, and Ivanov used his result here to prove that the automorphisms of the mapping class group are isomorphic to the extended mapping class group, which comes via conjugation. Much more recently, there was a similar result by Long, Margulies, Van Verburn, and Yao, uh, along with Kimura and Kuno, and myself and Wadwa, Wang, and Zhang for different types of surfaces. But this was the original group of authors to prove a very similar result for automorphisms of fine curve graphs. Right. And we can ask, well, the same exact theorem with the same exact proof methods might be a little difficult to extend, but potentially we can prove future structure theorems from this direction. So far we've talked about the geometry of these graphs and one direction of the combinatorics of these graphs. So the next thing that we could potentially ask is, all right, what about the topology? Well, graphs are one-dimensional objects, practically speaking. And so if you want to look at things like a homotopy type of an infinite graph, well, you're probably going to just have a bouquet of circles and probably infinite bouquet of circles. That's kind of boring. So what we're going to do is we're going to soup things up and create higher dimensional simplicial complexes from our graphs. How are we going to do that? Well, we're going to start with our graphs, and whenever we see k+1 disjoint curves or disjoint homotopy classes, we're going to fill them in with a k-simplex. So visually, that might look something like this. Well, we can also see here that things get a little bit more difficult to draw as we start filling in higher dimensional simplices. So with that in mind, we now have a higher dimensional simplicial complex. So whenever I'm talking about topology and I say fine curve graph, I actually just mean fine curve complex, so with everything filled in. So on the side of curve graphs or curve complexes, it was proven by Harrer that the curve complex is homotopy equivalent to a wedge of a non-trivial wedge of same-dimensional spheres, and this function is a function of the number of genus and the number of boundary components of your surface. This result in general is a stepping stone in proving the homological stability of the mapping class group, but there are many, many, many expositions of this result since, and many different types of kind of proofs. Right. Something that is a new result is actually about the homotopy type of the fine curve complex. And we actually have a very similar result that the fine curve complex is homotopy equivalent to a wedge of same dimensional spheres. And this is a new result joined with Ryan Dickman, Zach Himes, and Alex Nolte. The reason that maybe this wasn't as expected is because, well, we know that the fine curve complex itself, or sorry, the curve complex itself is finite dimensional. And it's finite dimensional as a function of G and B. However, the fine curve complex is infinite dimensional because it has simplices of arbitrarily high dimension. There is something to be said here. So let's see how we might try and prove such a result. Ah, Well, there exists a map from the fine curve complex to the curve complex, and in some sense the natural map. It takes a curve and sends it to its homotopy class. Like it's what we'd hope. And the second hope that we'd have is somehow this map creates a deeper tie between the fine curve graph and the curve graph. And in fact, it does. Uh, this collapsing map is indeed a homotopy equivalence, and so that allows us to have a result. Now, I want to make it clear, I do not believe that this map is a deformation retraction. I think it is just a homotopy equivalence, but that is not a proof. That is like conjecture. Huh. So let's see the stepping stones in proving that this is a homotopy equivalence. Um, well, one thing that we have is that if we have a simplicial complex and a simplicial map F, which ours is, and we have that the preimage of and every simplex is contractible, then F itself is a homotopy equivalence. Well, that allows us to show, reduce our problem to showing that the preimage of any simplex is contractible. But how can we do that? Well, one way to do that is if we take the continuous image of any sphere into the preimage of a simplex, it's enough to show that it's null homotopic for all simplices by using Whitehead's theorem and also citing the fact that the fine curve complex is a CW complex. So really, we're reduced to practically speaking, just showing this, that any sphere, is how I'm going to say it, in the preimage of a simplex is null homotopic. And really, there is something that's hidden here, and it's the following lemma, which I will say makes sense that it's true. And it's given any finite collection of curves, there is another curve that intersects them all transversely or finitely many times, all at crossing intersections. Because the word transverse doesn't mean too much if we're not talking about smooth objects. Right. And in fact, although this makes sense, it is actually non-trivial lemma to prove constructively. So like actually construct our curve gamma. And moreover, to prove this, we actually use a lot of like just straight up point set topology. And in fact, it is also a very useful lemma because it can be used to prove various topological combinatorial results about curve graphs. And pretty soon it's going to be geometric results as well. When we're trying to prove that the image of any sphere is null homotopic in the preimage of any simplex, that is going to be done in two steps. Because really what we want to do is we want to take a look at a sphere and then we want to shrink it, really, because we want to show it's null homotopic. So the first thing we're going to do is we're going to deform a sphere into simplices that are spanned by transverse vertices, so curves that are transverse, because we don't like things that intersect infinitely many times. And then once we have vertices that are transverse, we're going to just flow down to the star of one vertex. So how are we going to basically do all our flows? So this is going to be the method behind our madness all the time. Um, and what we're going to do is, well, if we have a sphere in the span of a few vertices, we're practically speaking going to uh, introduce a higher dimensional simplex and flow along that from one face of that simplex to another. Um, and we're going to use lemma 0 to practically speaking just choose how to add the extra simplices. And we're going to just keep doing that until everything is transverse. I am skipping some steps here. So one by one, we're going to practically speaking just make sure things are transverse by flowing across higher dimensional simplices. Then to look at an algorithm that flows us to the star of a vertex, well, what's a star of a vertex? You look at a vertex and its neighborhood and the subcomplex induced by that, which is contractible. So it's enough to show that you're live in a star of a vertex because you can use the contraction of the star to get a contraction of your sphere. Uh, and moreover, you're in the star of a vertex if you're disjoint from a particular curve. So we want to be disjoint from a curve. Um, but what is the preimage of a simplex? Well, it's the collection of disjoint homotopy classes. Uh, and so it's all curves that can be homotoped to be disjoint. And in particular, we use this can be homotoped to be disjoint to build our flow into the star of a vertex. In particular, what do intersections now look like? Any intersection should look like a bygone, and we can homotope it out. So how do we do this again? Well, we do the same trick of, oh, let's get ourselves to a larger simplex and then flow from one face to another. So in particular, uh, how can we decide what order to do this in? Well, if we fix a curve V4, we're going to be doesn't matter which one it is, but we're going to choose V4. And we are going to try and flow ourselves into the star of V4. So we want to be disjoint. So in other words, we want to resolve anything that looks like this little shaded region, these bygones. So how do we do that? Well, by choosing an innermost bygone, there can be multiple. So it's a bygone that does not contain another bygone on its inside. Uh, we can homotope across it and so start replacing curves with their homotoped versions. And this has to be done pretty carefully, but at the end of the day, what this means is that we can actually accomplish this replacement. Right. So what have we practically speaking done? We've taken any sphere in the preimage of a simplex and we've shown that it's null homotopic, which combined with Whitehead's theorem shows that our complex is contractible, or the preimage of any simplex is contractible. And if the preimage of any simplex is contractible, then we have a homotopy equivalence. So that's how all these pieces fit together. And what this does for me at least is that it kind of completes this table of trying to find similar results when we look at curve graphs and fine curve graphs, because if we can leverage what we know about an object that has been studied for many years, like the curve graph, we can potentially learn more about the fine curve graph and homeomorphism groups in general. Thank you.
Thank you for this nice presentation. Let me now stop the recording.